So I'm going to get moving. A bunch of stuff coming in. I'm going to begin with one that's not on relativity per se, but one that was in the news. A number of people have asked, in particular, someone whose name I'm probably going to pronounce incorrectly, sorry. Faisal Elian from Facebook wanted to have some explanation of this discovery in the news having to do with the Big Bang, right? You may have seen the picture. Let me just quickly show it to you. I don't know if you can see it right here, but this picture here, swirling pattern in the microwave background radiation, what's that all about? Well, we have been struggling for a very long time to gain insight into how the universe began. And as some of you no doubt know, there's a wonderful proposal that has really been in the textbooks, the good textbooks, for 30 years now, called inflationary cosmology. And inflationary cosmology makes use of a wonderful feature of Einstein's theory of gravity. That's the general theory of relativity. Many of you are in the special relativity course that I'm teaching, the math and non-math versions. Regardless, that is the version of relativity that Einstein came up with first in 1905. 1915, he went further in the general theory of relativity and gave us a theory of gravity. And it's a wonderful theory, and I'm going to teach a course on it at some point, but not yet. But let me just emphasize one feature of general relativity that doesn't get as much airtime as perhaps it deserves, which is in Einstein's version of gravity, gravity can actually be repulsive. It can push things apart. It can push outwards. And that is vital because we think that outward pushing of gravity might be what the Big Bang was. That might be the bang, if you will, in the Big Bang. So this has been the idea for a long time, that space might be filled with a substance, a fuel, called the inflaton field. The inflaton field, unlike the sun or the earth, gives rise to repulsive gravity, pushing everything apart. Now, how would you test that? Well, here's the thing. If space underwent the incredible stretching that the inflationary theory predicts, then little quantum processes in the early universe would get stretched out by that powerful stretching of space, and in some sense would get smeared across the sky. Now, if that happened, we should be able to see the imprint of those quantum processes today through dedicated observations of deep space. And that's what has happened on Monday. The announcement on Monday is that some very detailed observations of the sky, a telescope that has been in place in the South Pole for 3 years, have seen the imprints of tiny quantum ripples to the fabric of space. They're called gravitational waves. And these little ripples to the fabric of space wind up leaving an imprint on heat left over from the Big Bang. It's called the microwave background radiation. And the pattern that the theory predicts would look something like this, little swirling patterns in the microwave background radiation. And after 3 years of dedicated observations of this patch of south polar sky, the observers believe that they have now seen evidence of the swirling pattern, evidence of these tiny ripples in the fabric of space stretched by inflationary expansion. So this has now given us a great deal of confidence in the inflationary theory, given us a window into quantum processes taking place in the beginning of the universe, and it's a spectacular new era for cosmology and observational astronomy trying to peer back to the briefest moment after the Big Bang. Okay, that's the news. That's what that is all about. Let me move on to another question that has perhaps a little bit closer to do with the relativity course, and I'll bounce back and forth. This does not need to be focused on relativity per se. But a Facebook question has asked us the following, which is, in the special relativity course, I described how motion is always relative, part of where the notion of relativity comes from in special relativity. And I took it a little further and said, look, we always say that it is the Earth that goes around the sun, but if all motion is relative, then in some sense, you can take the perspective of us earth-bound beings and say it's the sun that goes around the Earth. Now, normally you hear the sun goes around the Earth and you start to think craziness, nuttiness, and part of what we learned in relativity is that it's not really nutty to take the perspective of those folks on Earth and indeed say that it's the sun that goes around us. That's a perfectly valid perspective. But I need to qualify that by the following important point also emphasized in the course, which is that when we are talking about motion that's not constant speed in a fixed direction, that is not constant velocity motion, that's motion that can be felt. That's accelerated motion. And so us beings on Earth, we in principle really can feel that the Earth is accelerating because it's not moving in a fixed direction at a fixed speed. Now, the acceleration is small, and that's why we don't literally become aware of it in everyday life. But look, just think of an amusement park ride where you're spinning around some center. You certainly feel that spinning motion. So that establishes that even if you don't feel the Earth's motion around the sun or the Earth spinning, if you don't feel that in everyday life, that's only because it's kind of feeble, and that's why our senses aren't directly attuned to it. But in principle, you could. Now, if you're on the sun, and let's just call the sun the center of this motion, the sun wouldn't feel, a person on the sun wouldn't feel that accelerated motion, and therefore, from the perspective of special relativity, that's the perspective, the sun's perspective, the constant velocity perspective that we would focus our attention on. It makes our calculations easier. It makes our description simpler, right? Long time ago, people tried to describe the solar system from the Earth's vantage point and had to have all these epicycles where this planet is moving around this trajectory, and it got very messy and confusing until people, like Copernicus and Kepler came along and showed that, taking the sun as the center simplifies the discussion enormously, and that's why that perspective is the one that is most natural, most sensible. But from the standpoint of relativity, yeah, if you're not worried about constant velocity motion, any observational vantage point is as good as any other, so you are justified in saying that it's the sun that goes around the Earth. Alrighty, moving straight onwards. Facebook, we have a question from someone whose last name is Sahu, S-A-H-O-O. Sorry if I mispronounce anybody's names, unintentional. The question is, if F equals ma, a little more technical question, if F equals ma, then why does the force to push a car depend on its speed, right? So let me just unpack that question for those of you who may have forgotten your Newtonian physics. The question is really, questioner is asking this. When I explain why it is that no object can go up to the speed of light and beyond, I'm fond of explaining it in loose language in the following way. Einstein taught us that as an object goes faster and faster, its mass gets bigger and bigger. If its mass gets bigger, then it takes a bigger push to make it go faster still. And in fact, according to Einstein's equations, as an object approaches the speed of light itself, its mass soars up to infinity, which means you need an infinite push to make it go up to the speed of light and beyond. And since there are no infinite pushes, nothing can go faster than the speed of light. Now to the question that Mr. or Miss Sahu asks, which is, in Newton's physics, F equals ma, force equals mass times acceleration. Now there doesn't seem to be a speed in there. It's just acceleration that dictates the force. So where does v, where does velocity, where does speed come into that equation? And what we learn, and in fact if you're taking the math version of the special relativity course, we'll discuss it in great detail toward the end of the course, F equals ma is not the right equation according to Einstein's relativity. The real way of thinking about it is F equals dp dt or dp d tau, depending on your understanding of calculus and the way you want to phrase these equations. But the bottom line way of thinking about it is that since, in some sense, mass depends upon speed, in Newton's equation, it's not just m times a, a fixed number times a. Think of that m as itself being dependent on v. And in that way, you see that the force gets larger as v gets larger because the m gets larger. Now, using that language can get you into a little bit of trouble when you try to implement that mathematically. And the alternate formulation in terms of momentum, and the rate of change of momentum with respect to time, or proper time, as we'll talk about later in the course, is the right way of talking about it. But intuitively, roughly, yeah, take F equals ma, imagine that m itself depends on v. That's where the dependence on the speed of an object enters into the discussion. Alrighty, so let me see if there's any cool stuff that we can talk about in here. So, alright, so I see right here, Kit Blank asks us, can you explain the inflaton and how it relates to gravity in more detail? How does gravity reverse? By reverse, I think that Kit is referring to gravity being repulsive and not attractive. And is there a way that we can recreate it? Yes, I know that, Kit, you would like to create your anti-gravity machine, so can you do that? All right, so the quick answer to the second question, can we recreate it, is I don't know, probably not. But people have actually asked themselves the question, serious people, even Alan Guth, who's the one who came up with this whole inflationary cosmology, wrote a number of papers years ago on the question of, could you create a universe in the laboratory? Here's what he meant, what he and his collaborators, I should say, meant by that is this. So the gravity, as I was talking about before, of the Earth, the Sun, the Moon, a comet, a rock, that's ordinary attractive gravity. We all know about that since the time of Isaac Newton. Where Einstein came in, he said that if you consider the gravity created not by a clump of matter, a rock, be it an ordinary rock or a rock the size of the Earth, if you're not considering the gravity generated by a clump, but instead the gravity generated by an energy that is uniformly suffusing space. Think of a steam bath where steam is uniformly filling the room. So imagine energy is uniformly filling a region of space. Then the equations of general relativity show that the gravity associated with that source, not the clump, but the uniform energy filling space, that will be repulsive gravity. Now, if you want me to explain where that comes from, that's tough for me to do non-mathematically, and it would take me a little far afield. I did an attempt of that in, I believe, my second book called The Fabric of the Cosmos. This is not a plug to buy it. Go to Amazon and search for inflaton field. You'll be able to read it for free on Amazon or in Google Books, that little section. It has to do with the pressure associated with this energy being negative. And it's that negative pressure ultimately that feeds in and gives us repulsive gravity. But the question is, could we make use of this to recreate repulsive gravity? The density associated with this inflaton field is enormous. I forget, I've done calculations, it's all rough, back of the envelope anyway, but something like 10 to the 94 grams per cubic centimeter. That's the equivalent amount of mass per each cubic centimeter that was in play during the inflationary expansion of the cosmos. That number is so spectacularly huge that it's hard to imagine how we could ever engineer to recreate the conditions that would build a universe of that sort. But theoretically, is it possible? Hard to say no, but certainly it's not going to happen anytime soon. All right, what else do we have here? All right, Alyssa Jarvis. What would have been before the Big Bang? So I'm actually reading off of the live stream comments right here. If there was nothing, then how did the Big Bang originate from that? Right, so, I mean, that's a good question. So first off, we should say straight out, we don't understand the very beginning, the very creation of the universe. That, at the moment, is one of those unsolved questions, and we're working really hard to try to get insight. And the announcement on Monday of the detection of these ripples in the fabric of space associated with inflationary cosmology, that's a big step forward. But it's certainly the case that it's not, at the moment, possible from a scientific perspective to definitively say how the universe began. Okay, that's out on the table. Now, there are, of course, various ideas that we have been developing to try to address these issues. One possibility to address your question directly is there might not have been a before the Big Bang. it could have been that time itself came into existence with the Big Bang itself, right? I mean, the notion of before is a temporal, a time notion. And if there was no notion of time until the Big Bang happened, then the very concept of before would be meaningless. I mean, there's a great little analogy. I don't know who it's to. I like to use it myself. I think Stephen Hawking may have been the first one to use this. But by analogy, imagine that you're on the surface of the Earth and you want to know what direction is north. So you ask somebody, you walk by them and say, which way is north? They say that way. You head north. You continue to walk. You pass by somebody else and you say, I want to head further north. How do I do it? They say, well, just head in that direction. You continue walking. When you get to the North Pole itself and you ask somebody right there, you say, hey, I want to go further north. How do I do it? At that point, they look at you a little bit strange, right? They say, what do you mean go further north than the North Pole? This is where north begins. There's no concept of going further north than the North Pole. Maybe that very idea, simple though it might be, applies to time. We can talk about 100 years ago, 1 billion years ago, 10 billion years ago, whatever, but when we get right to the Big Bang itself and you want to go before it, that may be as nonsensical as going further north than the North Pole. That may be where time itself starts. So that's one possibility, but it's not the only possibility. At the extreme other end of thinking about things, it could be that there are many Big Bangs, many universes, and in some sense, this collection of universes might exist forever, constantly generating new, expanding realms of space. That's one of the other, possible implications of the inflationary theory that we have gotten this insight into on Monday. And if that's the case, then from some global perspective, maybe the universe is eternal and always was and always will be. And the very question of the start may be meaningless because there was no start. The universe always was. Anyway, just to give you two extreme answers to a very important question, and the answer may either be one of those or someplace in the middle. Okay, so what else have we got? Let me just refresh here if you do. Oop, maybe I shouldn't have done that. Oh, can you guys still see me or are you guys gone? Well, hopefully you guys are still seeing me because I don't see you guys any longer. But in some sense, I never saw you in the first place. I just saw a little sign telling me you were there. So I'm going to assume that you still are and keep on going. Okay, so here's a question about relativity. And this one is a question that comes to mind to many people who learn the fact that a clock in motion ticks off time slower and slower. Because if you envision looking at that clock and it's ticking off time slower and slower, the natural question is, what about someone who's with the clock itself? And they look back at your clock, and from their perspective, it's your clock that's in motion, and therefore your clock should be ticking off time more slowly than theirs, right? So you can imagine that you're in a train, and you look out of the train, and there's a clock on the platform. From your perspective on the train, it's the platform clock that's moving, and therefore it should be ticking off time more slowly. That would seem to yield a contradiction. How can the person on the platform say the person on the train has a clock that ticks off time slowly, and the person on the train say the person on the platform has a clock that's ticking off time slowly? That would seem to be nonsensical. And actually it's not. Relativity is a spectacularly tight logical structure that allows both of those statements to be true. Now, for a quick way of thinking about it, which is by no means a perfect explanation or even a really good analogy, but just sort of gets your mind in the right place, think of the spatial version of that story, right? So let's imagine that you and I are near one another, and let's say we're roughly the same height. As we separate, you go far away from me and I go far away from you, I look at you in the distance and I say, whoa, you're really tiny out there on the field far away from me. And you looking back at me, you say, whoa, you look really tiny way out there on the field far away. Each of us is saying that the other is tiny. Is that a contradiction? No. That's a perfectly valid and sensible description of that situation in the spatial domain. In the temporal domain, it turns out a very similar feature holds too. I say that your clock is going slow, you say that mine is going slow. And there's no logical paradox that emerges from that. Now let me just take it a little bit further. If you were to go out moving in your train and then turn around and come back, the whole time I'd be looking at your clock thinking it was ticking off time slow compared to mine. But when we get back together, the question is whose clock will show more or less elapsed time. Now there's a come to reckoning when the two clocks come back together. And what turns out, and this is what we'll discuss in detail in the twin paradox later in the course, the person who goes out and turns around and comes back, for a moment at least, is feeling an acceleration. They are no longer traveling at a fixed speed in a fixed direction. And that is what distinguishes, breaks the symmetry between the two clocks. And as we will show, the clock that experiences the acceleration can no longer claim to have been at rest throughout this whole scenario. Therefore, their claims that it was the other clock in the platform back on Earth that was ticking off time slowly, those claims have to be discounted because the observational vantage point no longer adheres to the specification of moving at a fixed speed in a fixed direction. Which means when the person on the train or the rocket turns around and comes back, they will definitively be the one whose clock was ticking off time slowly. They will be younger when they return than you would have thought based on the amount of time that has elapsed on Earth. So literally, the way it's framed in terms of the twin paradox, two twins on Earth. They're both 21 years old. One zips off into space. 99.99999% of the speed of light, goes out for 6 months, turns around and comes back for 6 more months according to their clock on the rocket ship. When they step off the rocket, much more than 6 months plus 6 months, much more than 1 year will have gone by on Earth. Thousands, hundreds of thousands of years will have gone by on Earth depending on how quickly they went, how close they got to the speed of light. So it's an amazing fact. It's a kind of scientific version of time travel emerging from Einstein's ideas, which is a wondrous idea, and we'll discuss it in great detail in the twin paradox section of the course later on, but those are the essential ideas. All right, what else have we got here? I think I've got a email question. What is this email question? All right, so it looks like it's a Twitter question, actually, passed on to me by email from my handy helper in the other room. Oh, look at that. So if I leave Earth at high speed, to me, Earth looks like the one moving away. If I return, why am I the one who ages less? I just answered your question. So that was from Remster Cat. So I don't need to go through it again, but just give you the 5-second summary. Why is it that you are the one whose clock has advanced less, shows less elapsed time? You are the one that turned around and came back. You are the one that is accelerated. That is why you are younger. All right, let me look at another question coming in to us from, this looks like it's a Twitter question. Which discovery is most important? We are asked by Twitter person TZVIR. I don't know how to pronounce that. The Higgs boson or gravitational waves, which is more important? And you know what? I understand the motivation to ask questions like that, which is more important, because you want to get a feel for where in the pantheon of discoveries, this big announcement on Monday, where it actually ranks. It ranks high, real high. So in terms of, is it Nobel Prize worthy? Yeah, it really is. So the Higgs boson discovery, that is a discovery that its prediction was rewarded with the Nobel Prize. Fantastic. This discovery should potentially be rewarded with a Nobel Prize too. Have to see what happens. So it's Nobel Prize worthy, but saying which is more important, which is less important, it gets kind of silly after a while. These are vital, important insights into the way the universe works. The Higgs boson taught us how mass works. The discovery on Monday, the ripples in the fabric of space, are giving us insight into how cosmology works, how the universe began. All of it is important. Don't really need to say which is more important. All right, so back to Facebook. What do we got here? If simultaneity is relative, Julian Schlesinger asks, can time be said to have a direction? Yeah, that's a good question. So first off, when we say that time has a direction, I think we all know what we mean by that. Time seems to have a direction from the past into the future. We use all sorts of metaphors. The flow of time, the arrow of time, right? The arrow of time is pointing from the past into the future. But the question is, once we learn that different observers will have different conceptions of time, they'll have different conceptions of now, they'll have different conceptions of what things are happening at the same moment, is there then still a notion of a direction to time, or does that get thrown out the window? And the answer is that it does not get thrown out the window. It gets refined, but it's still there in the following sense. There's a notion of causality in reality, which is that something happens which is the cause of some future effect, right? You know, this can be anything at all. I take a rock and I throw it and I break a window, right? The cause, my throwing, yields the effect of the window breaking. And you might ask yourself, if time has all these weird, unexpected features in relativity, is it the case that everyone will agree on what cause yields what effect? Or might it be the case that different observers will say, hey, no, what you call the cause, I call the effect, and what you call the effect, I call the cause, and therefore the notion that there's a direction to time pointing from cause to effect, that would go out the window if, indeed, different observers could not agree on cause and effect. But the wonderful thing about special relativity is that, yes, it definitely revolutionizes our understanding of time. It upends our conception of what time is and its properties, but it does not in any way upend the notion of cause and effect. So every single observer in the universe, regardless of their motion, so long as it's less than the speed of light, and that would be the case for any ordinary observer that we have any conception of, they will all agree on cause and effect. If I say that I threw the rock, from my perspective, I threw the rock and it caused the window to break, then every observer will also agree that the rock throwing happened before the window broke. The arrow going from the cause in the past to the effect in the future, everybody will agree on that. Critical point. Thank you, Julian Schlesinger, for that question, bringing that point up to our discussion here. All right, Twitter. If gravity slows time, does passing through galactic equator planetary alignment have an effect to time on Earth? So this is Micro 101. And the answer is yes, in principle. So it's absolutely the case, and this is again not a special relativity effect. This is a general relativity effect. So those in the special relativity course who are now struggling or hopefully excitedly dealing with all of the weirdness of time and special relativity, we have not discussed this in the class, and I probably won't, but I will ultimately in the general relativity course. But what we learn is that gravity itself has an effect on time. And roughly speaking, the stronger the gravitational pull, or footnote, the stronger the gravitational potential, well, let me just talk loosely, the stronger the gravitational pull, the slower time elapses. So as a rough mental mnemonic, gravity kind of pulls on time, not only space, causing it to warp and curve, one of the key insights of general relativity, but gravity also pulls on time, slowing its passage. Now what does that mean? Well, it means that if you hang out near the edge of a black hole, time for you will go slower, elapse more slowly than time for people far away from the black hole. Now that's an extreme example, but any situation in which the gravitational potential, roughly speaking, the gravitational force gets stronger, time will tick off more slowly. So yes, even here, time on Earth in principle is affected by how high you are above the Earth's surface. Right at the surface of the Earth, gravity is a little bit stronger than, say, 1,000 feet floating above the surface of the Earth. So time elapses more slowly on the ground than it does, say, at the top of a tall skyscraper. and any other effect. The questioner asked various things about the Earth's motion and passing through environments, which would affect the gravity on Earth by virtue of the influence of the gravitational pull of other objects. Yes, in principle, that does affect the passage of time. So absolutely yes. Alrighty, so let's see what else we've got questions-wise. All right, I have a multiverse question I think we have here. Okay, so the question that Erica the Redhead. So Erica the Redhead, if you are still with us, you ask, regarding the new inflationary data, how does this tie into the multiverse theory? It appears that scientists are split on the issue. And Erica, you're absolutely right. Scientists are split on this issue. And I would frame it this way. The most important thing to learn from the data that was released on Monday is that we think we know what we're doing when we write down equations describing the earliest moments of the universe, right? We play with these equations, play with them for decades, and you never know if they are just math on a piece of paper or if they're really describing reality. The data seems to suggest that the equations are describing reality. So that's exciting, right? We think we know what we're doing. Now, the thing is, when we study the inflationary theory, the set of equations that the data on Monday was speaking to, the inflationary theory almost always, and there's some asterisks I should give there, but roughly speaking, the inflationary theory almost always ensures that our Big Bang is not the only Big Bang, that there will be other Big Bangs yielding other universes, that we would be part of a multiverse. And in fact, there's even a less dramatic way that the inflationary theory can yield a multiverse. It seems to suggest that space would be infinite. And if space goes on infinitely far, you can also argue that region by region by region, there will be separate universes, some of which would actually be duplicates of the universe that we see here. So if you're interested in those background ideas, many places you can read about it. The Hidden Reality, one of my books, again, I hate people who plug their stuff. I'm not plugging my book, but if you go again to Amazon or Google Books, just read the first few pages online. It's all about this idea of an infinite universe giving rise to realms that would be duplicates of ours. Okay, that's the background. The question, with all of that as the background, do we physicists now think that since the data is supporting inflation, and inflation seems to yield a multiverse, that we now have greater confidence in the multiverse? Some do feel that way very strongly. I am much more on the fence, and I don't mean to be equivocal here, but when I look at the inflationary theory and the multiverse that it gives rise to, I see various technical issues. Let me just raise one off the cuff, which is the other universes in the inflationary multiverse would have different features typically from ours, at least in the versions of the inflationary theory that meld it with rich theories of particle physics or string theory. These other realms could have different kinds of particles and different kinds of forces. So here's the thing. If the inflationary multiverse says that there could be all these different universes with all these different features, what does it really predict? How does it predict our universe? How does it tell us anything about what we observe here if there are so many other possibilities that it predicts too? Now, this is a problem that physicists know about and have been working to solve for a long time. This is an active area of research, and I would say that we still don't have the answer to it. Some people invoke something called anthropic reasoning, which says, hey, those other universes, they'd be so different from ours that our form of life couldn't exist there, and that's why we live here and not there. So we have to include in our analysis the existence of observers like ourselves. Many scientists aren't comfortable with that kind of reasoning. They don't like having to bring in this additional feature of our own existence. It feels almost circular to some or a cop-out to others. I don't feel that way. I think this is valid reasoning, but I'm not ready to take it on board as easily as some of my colleagues. So bottom line is this. We have increased confidence in the inflationary theory. We still need to work on the underlying theoretical math and ideas behind the inflationary multiverse before we take that on board as strongly as the inflationary theory itself. So I think that's pretty much where that issue of the multiverse stands. All right, Erica, thank you for that. I'm starting to feel like a talk show host. Oh, Erica, thank you very much for your question. Let me just move on to George Salas, who has given us a question from Facebook. And he refers to my friend Lawrence Krauss. And he says, Lawrence Krauss refers to string theory as beautiful and elegant math, but mentions that it has no predictive capability, and thus possibly a dead end, and perhaps even a groundless theory. What are your thoughts on this? Well, Lawrence is a good friend of mine. We've debated this issue, I don't know, like a dozen times in public forums. You can see them on YouTube, some of them. And here's my thinking. String theory is very much a theory in development. And some people say, well, you've been working on it for such a long time, so where are the definite predictions that any good physical theory should give rise to? And look, the answer to that is, we've been working on string theory for, I don't know, roughly 30 years. I started working on it in the 80s. I was a graduate student. That was pretty much when it was just bubbling up into consciousness of most physicists. 30 years might seem like a long time from the standpoint of an individual human, but when you're trying to answer deep questions like how do you put gravity and quantum mechanics together, a theory that might really be able to give us insight into the very beginning of the universe and how matter works on its most fundamental scales, well, 30 years is a drop in the bucket when you're talking about trying to answer those kind of deep questions. So, look, our goal is to get to a point where we can make definitive predictions like this thing here. So my coffee cup, right? I don't know if you can see that. See those equations there? That's the standard model of particle physics. That's like, the gold standard of a theory whose equations give rise to predictions, like the Higgs boson that was found at the Large Hadron Collider. We have equations for string theory. We're trying to understand them. And as we go forward, we hope to hone in on definitive predictions. But I'm the first one to say that right now, as of today, it's very hard to falsify string theory. There's almost no, and that's not completely true, but there's almost no observation that would rule the theory out. Now, that is not something we're happy about. If the theory is wrong, we'd all like to know so that we could work on a theory that has a chance of being correct. But being that as the state of affairs, what we do is we work hard. We work on the equations. We push forward. We try to understand what this theory is telling us about reality, and in that way extract, hopefully, one day predictions that can be confirmed or refuted. That is the nature of cutting-edge science. So as long as we continue to make progress, as long as we're heading toward that hoped-for day when the theory will have a reckoning with observation and data, well, we just keep on going. Now, if that doesn't please a given researcher, they're free to move on to work on other things, and many have done that. Those who stay the course are the ones that feel that there's enough exciting developments to continue to push forward, and certainly I'm one of those people. Okay, so George, thank you. Let me just look what else we got here. So we have Martin van Heringen. Sorry, I know I just completely ruined your name. Dutch name, no doubt. Do you believe, like Gerard 't Hooft, Nobel laureate physicist from the Netherlands, that there must be a smaller causal world lurking behind quantum mechanics, so that quantum mechanics only gives the illusion of randomness? So, Martin, that's a real deep question, and Gerard 't Hooft has been one of the few people who's really been pushing this line of research, basically saying that quantum mechanics is not the be-all, end-all theory of the micro realm, right? I mean, Einstein himself famously had difficulty accepting quantum mechanics. He did not like the probabilistic nature of the theory. He did not like other features of the theory, like quantum entanglement, which he felt strongly suggested that the theory, even if it was giving accurate predictions, was not the deepest, most complete fundamental theory of the universe. And Gerard 't Hooft has been pushing a similar line of thought, that the probabilistic random nature of quantum mechanics rests upon a deeper foundation. And if we understood that deeper foundation, we might not need to use the language of probability, right? I mean, it's kind of similar when you listen to the weather report and the weatherman. I don't know, is that sexist? The weather person. the weather man, the weather woman, whatever the right language should be, when they say that there's a 50% chance of rain, you don't think to yourself, oh, okay, there's somebody out there flipping a coin that's going to determine whether or not it's going to rain. Instead, you say to yourself, I know what that means. The weather person doesn't have a complete understanding of the weather system, where all the particles are that will determine whether or not it's going to rain. So they parameterize their ignorance by saying, based on what we understand, it looks like there's a 50-50 chance that it's going to rain. Deep down, though, there's no probability in a classical description of the weather. Maybe that's the same thing with the probabilities in quantum mechanics, right? So Gerard and others have suggested maybe when we say there's a 30% chance the electron will be here and a 70% chance that it's over there, maybe deep down it's like the weather report. If we understood what was underneath it all, we wouldn't use the language of probability at all. I don't see any evidence for that yet. It would be a beautiful, profound, deeply transformative result were we to show that quantum mechanics really does result from this deeper underlying foundation, which doesn't involve probabilities. I've tried to read some of Gerard's papers. Perhaps I don't understand them fully, but as of yet, I don't see a convincing argument by any means that that perspective is correct. But I'm glad that somebody with great insight like Gerard Tuft is thinking about it. All right, a few more questions. What do we got here? So, from Facebook. All right, so Giancarlo Alvarez, I don't know if this is Facebook or Twitter, writes, with the recent news of gravitational waves making headlines all over the news and science outlets, everyone seems to be talking about the origin of the universe. I don't think we'll be around to see how it ends, but I'm curious as to your thoughts on how it will or won't end. Wow, Giancarlo, you feeling all right, man? It sounds like, the end, right? So, no, it's a great question. In fact, I have to tell you, it is one that I myself have been thinking about of late. And we can make a lot of predictions. They're not all solid, but we can make a lot of predictions about what the far future will be like. So, for instance, if you're talking about the end of the Earth, right, there's a chance that in, I don't know, about 1 trillion years, roughly speaking, maybe 500 billion or so, I should say, it's probably more like 5 to 10 billion. Let's call it 10 billion. Let's start simpler. So let's say in 5 to 10 billion years, the sun itself will grow really big, and it may swallow up the Earth, and that could be the end of the Earth. Or it could be that there's an interaction with other galaxies, say within, I don't know, 1 trillion years or so, and those interactions could cause the Earth to be flung out of orbit, and that would be a different kind of demise for the Earth. Or, if you do a calculation, this is an interesting one, that in about 100 billion years, the Earth will lose energy through emitting gravitational waves, those ripples in the fabric of space that were announced on Monday. So to tie into your question, it'll give off gravitational waves and spiral in to the sun. That's how the Earth might end. Now, if we go further, not just talk about the end of the Earth, but talk about the end of the universe, the way things currently look, it seems as though the universe is expanding ever more quickly over time. It used to be in the past we wondered maybe it'll expand for a while and then collapse back in a big crunch. Or maybe it'll expand ever more slowly toward the future and kind of peter out. Now it looks like it's going to expand faster and faster and continue to do so for eternity. Now, if that's not the case, if future observations show that the accelerated expansion that we now know about, if that decays and slows down, the answer would be quite different. But if the data holds up, that says the universe will get bigger and bigger and bigger, colder and colder and colder, less and less dense, more and more dilute over time, and will kind of end in kind of the most petered out way with particles just wafting through an ever bigger and ever colder universe. And that might be how it all ends. We don't know for sure, but that is the leading contender today. All right, what else have we got here? So, looks like it's from Twitter. Can you explain quantum entanglement? And does it break the speed of light? All right, so that is a real good question. And I think I'm going to have to make this my last one for today. And you should write in and let us know if you enjoyed the session, because these are fun for me to do. And if you guys are enjoying it, I'm happy to do them more frequently. In fact, we can have other people, some of the faculty that are going to teach the subsequent courses. It'd be fun to introduce them to you by having them do some live sessions. And the reason I'm going to make this my last question is because I actually have to go teach my own special relativity course at Columbia, where the students are using exactly the same online materials that you guys are using. The only difference is I meet with them once a week for a couple of hours, and now I'm meeting with you guys, so maybe there's no difference at all. But anyway, so on to this last question, explaining quantum entanglement. It's a big question, so I'm going to just give you sort of a quick thumbnail sketch, which is this. In quantum mechanics, we have learned that the following bizarre situation can occur. You can have two particles that are far apart in space, and yet a measurement on one particle over here, make believe it's in New York, say, a measurement on the particle in New York can have an influence on the particle in Los Angeles. Quantum entangles. It's as if there are threads of quantum influence that are invisible to us, but somehow thread the space between these two distant particles, correlating their behaviors. So for instance, if you measure this particle and you find some feature of it, say it's red, then this particle will definitely turn out to be blue because of the quantum link between them. Now, Einstein was one of the first people to point out that there could be quantum entanglement, a measurement on one object here affecting another object over there. And he parlayed that realization into an argument that quantum mechanics couldn't be the full story. He argued that if a measurement over here affects the outcome of an experiment over here, then it must be that secretly, even though quantum theory is based on probabilities, the outcome over here, even though quantum theory may have said there was a 50-50 chance that the particle would be red or blue, the fact that you measure it and find it blue, it must have been blue all along, according to Einstein. And therefore, the quantum mechanics 50-50 description, that only showed the weakness, the failure of quantum mechanics to be a complete description. That was Einstein's argument. But then a guy named John Bell came along in the 60s, and he showed, as far as we can tell, that Einstein's perspective wasn't right. That this flat-footed notion that you perform a measurement over here and it affects an object over here, that really happens in a way that Einstein would have thought weird. In fact, Einstein called it spooky action at a distance. It appears that the world is spooky. Now, the final part of Noid 04's question is, does entanglement break the speed of light barrier? It seems like it does, right? You perform a measurement in New York, it instantaneously affects this particle in Los Angeles. I should have said that. It seems to be that the effect is instantaneous. That would seem to be faster than the speed of light. But actually it's not. Relativity and the barrier of light speed survives by the skin of its teeth in this example, because you can show, and it's not too hard, that even though measuring the particle here seems to tickle the particle over there, it doesn't do so in a manner that allows any information to travel from New York to Los Angeles. Because of the randomness of quantum mechanics, the probabilistic nature of the theory, the only way you can extract information from the system is by comparing the results through a telephone call or bringing the experiments back together and see that every time this one was red, this one was blue, every time this one was blue, that one was red. You see this deep correlation in the results of the two experiments. But looking at any experiment, either in New York or in Los Angeles, in isolation, there's no information. It's just a random set of results. So there's no way that you can start in New York and say to the person in Los Angeles, hey, if you get blue, that means I'm telling you to sell IBM stock because I've just learned something over here in New York. Can't be done because you don't know what answer you're going to get, red or blue. Therefore, you don't know what answer your friend in Los Angeles is going to get on the measurement. You only know that if you get red, they get blue. If you get blue, they get red. So it's the correlation, the comparison of the two that holds the information. No information in any single measurement by itself. So in that sense, no information has gone from New York to Los Angeles instantaneously. Nothing in the sense of no information has gone faster than the speed of light. And that's the way we get out of that situation. If you are interested more in that, let me just point out, in Science Unplugged, even if you're not taking the courses, there's a whole section on quantum entanglement. So when we end the session or later on when you have time, go check out Science Unplugged, click on the theme button, look under quantum entanglement. I don't know, must have about 10 or 15 questions. which I give answers to a similar collection of questions and issues that allow you to understand this a little bit more fully than the answer that I just gave you now, perhaps, as well as all the other subjects too, quantum mechanics, cosmology. Much of what we discussed today, there are versions of the answers and answers to other similar questions that you can find in Science Unplugged. All right, so I'm going to sign off now. 2:15, I got to go teach, but let us know if this was fun, and we'd be happy to do another session of this sort in the not too distant future. All right, thanks a lot, guys. I'm going to try to find the button to get out of this. I don't know what button that is, but I'm going to hit something over here, and then I'm going to just sign off.